Good. Okay, welcome back, everyone. Before we continue, does anyone have questions for me? Okay, good. So we're going to continue with our introduction to probability, finishing up a few of the sort of basic rules that we started last class, and then look at a couple of sort of non-trivial computations. So calculating some probabilities that might be useful, and often, as many of these examples seem to come from the gambling world. So we'll see a couple of examples from cards and dice games. But here's a boring or easy lemma that you've seen before. And what is this A with a bar over it? This is the complement of A. And that's A bar is you take the whole set of possible outcomes and you take away A, and that's what's left. So what is this saying? It says you have a set S of outcomes. You have something in there, an event called A, which means it's a subset of S. And sometimes it turns out, rather than computing the probability that A happens directly, it's easier to compute the probability that not A happens. So that's this set out here of everything that's not included in A. Okay. Now, have we seen a rule like this before? What's the name of it? Yeah, it's the complement rule that says if I want to know the size of a set, I can take the size of the universe minus everything that's in the universe that's not in the set. Okay. So sometimes it's more convenient to do that, and we'll use that a couple of times today. And here's another one. For any two events, A and B, the probability of A or B, A union B, is equal to the probability of A plus the probability of B minus the probability of A and B. And the picture for that is this one. I have A, I have B. In general, A and B may have stuff in common. So if I'm interested in knowing what's the probability of A union B, so I land somewhere inside these two circles, I can figure that out if I know the probability of A, and I know the probability of B, and I know the probability of this common intersection. And as you saw, probability of A plus the probability of B, that counts. You know, the way you get probability of A is you add up the probabilities of the individual events, individual outcomes in A, and the way you get the probability of B is you add up the probabilities of the individual outcomes in B, and you notice that if you do that, then the ones that are in here, you have added their probabilities twice. So you've double counted the ones in here, and this just says get rid of one of those occurrences. So have we seen this one before? What's the name of it? So this is the principle of inclusion-exclusion. there we were talking about the sizes. The size of A union B is the size of A plus the size of B minus the size of A intersect B. And it's for the same, basically it's true for the same reason that the other one is true, that size of A plus the size of B double counts the contribution of points in the common intersection. All right. So questions about that? No? All right. So here's then an experiment for us. Let's take a probability space over the set 1 to 1,000, integers 1 through 1,000, and probability of I is equal to 1 over 1,000 for all I in S. So a uniform, call this a uniform distribution over this set of integers 1 through 1,000. So someone picks a random integer between 1 and 1,000. And let's say x is all of the values I in S, so integers from 1 to 1,000, such that I is divisible. Let me just write the formula. I mod 2 equals 0, or I mod 3 equals 0. So I is divisible by 2, or I is divisible by 3. That's the set that I'm interested in. And I would like to know, what is the probability of x? So I pick a random integer between 1 and 1,000, and I want to know what's the probability that it's divisible by 2, or the probability, or that it's divisible by 3. So how would we attack this? Yep.
Find the number, if you divide 1,000 by 2, and that's how many are divisible by 2.
Yep.
Divide by 3, so many are divisible by 3. You add those and subtract how many are divisible by 6.
Okay, good. So this is exactly the kind of thing that the principle inclusion-exclusion is perfect for. So we have a condition here which is an OR, which really means it's the union of two sets. And these two sets are the set A, which is I and S, such that I mod 2 equals 0. So these are the even ones. And this is the other one is the set B, such that of things in S, such that I mod 3 equals 0. So those are the ones that are divisible by 3. And notice that X is equal to A union B. Now the sets A and B are unfortunately not disjoint because some integers are divisible by 2 and some of them are divisible by 3. For example, 6, 12. Those are divisible by both of those things. So these are not disjoint sets. So we can't just use the sum rule, which means we have to use the principle of inclusion-exclusion. And so what is common? What is this set A intersect B? Well, this is the set I and S such that I mod 6 equals 0. Right? So if I'm an integer and I'm even, so I'm divisible by 2, and I'm also divisible by 3, that means if I first divide myself by 2, I'll get an integer, And that integer is still divisible by 3, so I can divide it by 3 and get an integer, which means that I'm divisible by 6, because I just divided by 2 and then divided again by 3 and got an integer, which is the same thing as dividing by 6. Okay? So the probability of x, according to the principle of inclusion-exclusion, is probability of A plus the probability of B minus the probability of A intersect B. What is the probability of A? Or how many integers are there in the range 1 through 1,000 that are even? So half of them are even, and that's because this range starts with an odd number and ends with an even number. So half of them, exactly half of them will be even. There's 1,000 of them, so exactly 500 of them will be even, which each one of them has probability 1 over 1,000. So if we add up all of those 500 probabilities, we get 500 over 1,000. Okay? So this is 500 over 1,000. How many integers in this range are divisible by 3? Yeah. Yeah. So that's a little bit trickier. There it kind of matters exactly how things start and how things end. But if you work it out carefully, you'll realize that there's exactly 333 of them. And since each one has a probability of 1 over 1,000, when you add up those 333 probabilities, you get 333 over 1,000. And then how many of the integers in this range are divisible by 6? Anybody know? Yeah. 166. So it's something like 1,000 divided by 6, but 1,000 divided by 6 is not an integer, and so you have to be a little careful. You'll realize it's actually the floor of 1,000 divided by 6. So this is 166 over 1,000, which is, let me just make sure I don't make a silly calculation error. 667 over 1,000. Okay. Yep. Yeah. So if I said, how many are divisible by 2? And how many are divisible by 12? It would be a different story. You'd have to be more careful, right? Because, well, and in fact, then it's just how many are divisible by 12, because everything that's divisible by 12 is also divisible by 2. So this works in this case because 2 and 3 are relatively prime, meaning they have no factors in common. But in general, if you give me, if the question here is with 2 relatively prime numbers, meaning they have no factors in common, so their greatest common divisor is 1, then you'll get exact product of those two things. That answer your question, kind of? Well, again, so if you're divisible by 45, then you are also divisible by 5. So this extra condition that you're divisible by 5 and you're divisible by 45, it doesn't add anything, right? So if you're divisible by 45, you're already counted in the divisible by 5 part. Okay. Yeah, where things get a little more tricky is when the two numbers are neither relatively prime and neither one is a multiple of the other. Then it gets it's a little bit different. But let's not worry too much about that. That's a good idea for an assignment question. So you can blame him if you get this as an assignment question. Okay. So what falls out of here is actually one of the most powerful things that we have available for us, even though it's trivial, and this is called the union bound. And that says that the probability of A union B is at most the probability of A plus the probability of B. Okay? And let's see why that's so obvious. Well, the probability of A union B is exactly the probability of A plus the probability of B minus the probability in the intersection. So if we don't bother to take away the stuff in the intersection, remember it has to be bigger than or equal to 0. It's not negative. So if we don't bother to take that away, then we're left with something that's bigger or at least as big, right? So that's the union bound. It comes immediately from the principle of inclusion-exclusion, and it has a generalization to when you have many sets, which is that the probability of A1 union A2 union and so on union AN is less than or equal to the sum I equals 1 to n of the probability of AI. So this is just applying the same result to many sets. Okay. And we saw that before when we were talking about the sizes of sets, that the size of A union B is not more than the size of A plus the size of B, and same thing for many sets. So if we're happy with an overestimate, or if the overestimate is good enough, then we don't have to deal with computing this thing. All right, and we'll see later in the course that that's ends up being really useful because very often this part is hard to compute exactly. And for many sets like this, that what comes after the sum of these probabilities is a whole mess of things that you have to compute. And sometimes we're very lucky and none of those things add up to much anyway. So we don't really need to bother computing them if we just want a rough upper bound. Okay. Questions? Good. Okay, so let's now I guess actually there's one more sort of obvious one that I won't even take up any more space on the boards with. If A is a subset of B, so that's a picture like this, you have A and you have B is containing A, then what do you think I'm going to tell you about the probabilities of A and B? What's the relationship between those probabilities? Yep. Probability of A is less than or equal to the probability of B. Right? Because subset already could mean A equals B, or that the stuff that's not in that's in B but not in A actually has 0 probability. That's allowed. So, but definitely the probability of A is less than or equal to the probability of B. And that's just because when we add up the probability of B, we add up all these individual probabilities of these individual outcomes, including all the ones that are in A. So we can only get something, something bigger. All right. So good news is what we did in the first part of this course is about to become very useful. And the reason for that is the following. We'll say that S, so a probability space, S PR, is a uniform probability space if the probability of W is equal to 1 over the size of S for all W in S. So what this says is the probability of a particular outcome is the same as the probability of any other particular outcome. And we saw already, once you tell me that all the outcomes have the same probability, that means I know what the probability is. It has to be 1 over the size of S, because the sums, one of the rules was that the sums of all these probabilities have to add up to 1. So that's called a uniform probability space. And almost everything that we've seen so far has been a uniform probability space. Right? We talked about rolling a 6-sided die twice, and there were 36 possible outcomes, 6 times 6 possible outcomes. Each one had probability 1 over 36. We just did an example where you pick a random number between 1 and 1,000, a random integer between 1 and 1,000, and each one was, we assumed that each one was equally likely. When we model coin tosses, we assume that heads and tails have the same probability. And when we modeled 2 coin tosses, we assumed that the 4 outcomes each had probability a quarter. So these things are come up all over the place. And in some sense, in any problem, there's usually one of these uniform probability spaces hiding maybe deep down behind the problem somewhere. Would anybody like to see an example of a non-uniform probability space? Yeah?
Wouldn't the addition of the 2 dice be the 7, only 7 have that?
Yep. So if I say the experiment is I roll 2 dice and take their sum, and that's the outcome of the experiment, then the outcome set is the integers 2 through 12, and it's not a uniform one, right? We saw that different outcomes have different probabilities. In fact, 7 has the highest probability. Okay. Here's another one. I'll just put it down here. S is the set of natural numbers. So for me, that means 1, 2, 3, and so on, up to, but not including infinity. And you use the probability function. Probability of I is equal to 1 over 2 to the I. So you can check, actually, that this thing satisfies the definitions of a probability space. So S is a countable set, so that makes it a possible outcome set. And this sum 1/2 plus 1/4 plus 1/8 plus 1/6 plus 1/16, and so on. That adds up to 1 like it's supposed to, and everything in it is non-negative. So indeed, this is a real probability space, and it's non-uniform. Anything else you might notice about this uniform probability space definition? Anything you can tell me about S? Well, if the probability of everything, each thing in S, is 1 over the size of S, then this must be well defined. And in particular, if S is infinite, then this would say that everybody has 0 probability in a uniform probability space. But then if I add up all the probabilities, I'll get 0, which doesn't work. So if I want a uniform probability space like this, I actually need S to be finite. So for example, I can't say the uniform distribution over positive integers, because it just doesn't make sense. Okay. So easy example. Anybody know this Lotto 649? Yep.
I just have a question about what you did on the natural numbers.
Yep.
What are you trying to figure out the probability of?
Nothing. I'm just saying this is a probability space. So
And what's the PR, like what's the probability of I if you wrote?
probability of I is 1 over 2 to the I.
What's I?
Any one of these natural numbers. So the probability of 1 is 1/2. Probability of 2 is 1/4. Probability of 3 is 1/8.
What does that mean? What is the probability of 1? What does that mean?
I mean, so when I say we talk about a probability space, that means there's a set S of possible outcomes, and each one of them is assigned a probability. And what's a probability? A probability is a number between 0 and 1, with the only rule that those probabilities all have to add up to 1. So this is an example of something that satisfies both those rules. Every probability is between 0 and 1, and if you add them all up, that sum is 1. 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. That infinite sum adds up to 1. It looks crazy, but actually no, this is a really common thing. For example, very closely related to this is how many times do I have to toss a coin before it comes up heads? So that's a probability space that looks very much like this. Yeah.
Wait, so it's not the probability of like choosing one out of the natural numbers? It's just
we just have definitions, and if you look at the definition of probability space, what we need is a countable non-empty set S. We've got that here. It's non-empty, and it's countable. In fact, by definition, so PR is a function from S onto real numbers. And remember, the two rules were that the probability of any particular thing is between 0 and 1. That's the first rule. And the second rule was that the sum over all of the things in S of the probability of that thing is equal to 1. Those are the only two rules for a probability space. So this is why I say that really the probability is about mathematics, and sometimes intuition is confusing here. But this is a probability space with an infinite number of possible outcomes. And it's not an insane one, because if you toss a coin and count how many times you have to toss it before it comes up heads, you get something that looks very much like this. In fact, it's just off by 1.
because the probability is the 1/2 correct?
Yeah, I mean, later we'll work that out, but that's basically it. Okay, anybody know this Lotto 649? No? So this is an Ontario lottery. What happens is they fill a ball with 49, or they fill a big, like a bingo style ball with 49 numbers. In fact, it's the integers. Each little ball has an integer on it, and that's the integer 1 through 49. And then they roll it around so it's super random, and 6 times they open a trap door and one ball falls out, and they roll it some more and they open a trap door and another ball falls out. And anyway, so the point is that those 6 balls that fall out, each one has a number on it, and well, any subset of 6 balls should be as likely as any other subset of 6 balls to fall out. And so what this is really saying is that the outcome is a subset of size 6 from the set 1, 2, 3 up to 49. Okay. So every outcome, and conversely, every subset of size 6 of 1 through 49 is a possible outcome for this lottery. So that means the outcome set S has size 49, choose 6. That's what this thing is supposed to be doing. It's choosing 6 numbers from this set 1 through 49. And I mean, there's no reason to think that any set of 6 numbers should be more likely than any other set of 6 numbers. So that should say that the probability of any particular outcome is 1 divided by 49 choose 6. Okay? So 1 over the size of S. And what's 49 choose 6? I don't know if I have it written down here. Yeah, no, I don't have it written down, but it doesn't matter. So it's an example of a uniform probability space. If you're going to play the lottery, you should know what this actual value of 49 choose 6 is, because you can use it to figure out how likely you are to win the lottery. And then if you know how much you win, you can use it to figure out whether it's worth playing or not. We'll see that when we do expected values. But one particular sort of strange thing about this is, it's not strange, but it maybe looks surprising. So in the Lotto 649, you get to choose 6 numbers. You get a little card, it's like a Scantron sheet. You choose the 6 numbers you want. And so you might as well choose people have all kinds of strategies. They use their birthdays and their grandchildren's birthdays or whatever. But a set of numbers like this, which looks like a reasonable thing on a lottery ticket, is just as likely to come up as this set of numbers. So if you're stuck picking lottery numbers, just scratch off the first 6 numbers, because you're just as likely to win as anyone else. The only danger there is if a lot of people do that and you do end up winning, you're going to have to share the prize with all those other people. That's the only good reason for taking weird-looking sets of numbers that are less likely to be picked by other people. But it doesn't increase your chances of winning. It just means if you do win, you won't have to split the money with so many people. Okay. So the good news is a lot of things come really, these uniform probability spaces come up all over the place. And, or I don't know, I'll call it a fact, is that for any, what do we call these, events, so you give me any subset of the possible outcomes. If I want to know its probability, well, actually, all I really need to know is the size of that set and the size of the total number of possible outcomes, right? Why is that? That's just because, remember, the probability of a set A is just equal to the sum of W in A of the probability of W, but that's, if it's a uniform probability space, this is W in A of 1 over the size of S, which just means it's the size of A over the size of S. Nothing terribly deep there. Why does that make us happy? Well, it makes us happy because we've just spent 2 assignments and a good chunk of the semester trying to do things like figure out the sizes of sets. And we have some rules, some ways to attack that. And so that means we can use those to attack questions about probability if it's a uniform probability space. So let's try that. Okay, so here's an example. A standard deck of cards. So this is 52 cards. Each card has a rank, and the ranks are ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. And in addition to a rank, it has a suit. And that suit is a heart, a diamond, a spade, or a club. And each of these combinations exists, right? So there are how many ranks? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Should be 13. I must have miscounted somewhere.
There's no 1 in the deck of cards.
Oh, there's no 1. It's the ace, yeah. Good point. So 13 of these. So there's 13 of these. There's 4 of these. And 13 times 4 is 52, so that's good. That's where the 52 cards come from. So every combination of these occurs. All right, that's the definition of a standard deck of cards, which many of you have seen before. Let's play some poker. So, so this, let's leave it like that. A full house is a set of 5 distinct cards. And with the following two conditions, 3 have the same rank, and the other 2 have the same rank. So for example, here's a full house, 7 of hearts, 7 of clubs, 7 of spades, queen of hearts, and the queen of diamonds. So that's an example. 3 cards have the same rank, and the other 2 also have the same rank as each other. Of course, the 2 ranks have to be different because otherwise we'd have 5 cards of the same rank, but there's only we only have 4 cards of the same rank for each rank. So that's a full house. And here's the question. Given 5 random cards from a deck, standard deck, so a 52 card deck, what is the probability of a full house? Okay. All right, so somebody shuffles the deck really carefully with a machine, so the deck is perfectly shuffled, meaning that every permutation is equally likely of those 52 cards, and then they throw you the top 5 cards on the deck, so that's 5 random cards, and you want to know, well, what's the probability that I get a full house? So this is a pretty strong hand in poker. If you play poker for money, it's good to know these things. All right, so we want to set this up as a probability question. So, set of 5 card subsets of a standard deck. Okay. And a subset of S is the set of full houses. So those are the 5 card subsets that have 3 of the same rank and 2, the other remaining 2 of the same rank. All right. So, and we're going to assume that, you know, if all the shuffling is done fairly and perfectly, there's no reason we should get any particular set of 5 cards is more likely than any other subset of 5 cards. So somehow we're going to say that the probability of any particular hand is equal to 1 divided by the number of possible hands. All right. So for that, we need to know the size of S. How many 5 card subsets of a 52 card set are there? Yeah. This is just right, a deck is 52, is a set of 52 items. 5. A deck is a set of 52 items, and we choose 5 of them. So that's the number of ways of doing that. I mean, that's the reason we call this when we say this out loud, we call this 52 choose 5. Okay? All right, so that's the size of S, and that's true for, this is true for every possible hand. All right, now we want to know, here's the set of full houses. We want to know what's the probability of that thing. So the probability that we're given a full house, this is a uniform probability space. So that's the number of full houses divided by the number of hands. So it's going to be the number of full houses divided by 52, choose 5. Now we leave the probability world and we're left with a counting problem, which is just counting how many full houses there are. So what are the counting rules we know? We've got, the sum rule, the complement rule, all of those things. But the real granddaddy, the really important one that we end up always using is the product rule, which means we should find a procedure, describe a procedure that can generate any full house such that every execution of the procedure generates a full house and 2 different executions generate different full houses and every full house can be generated by this. So how could you, if I wanted to write down a full house like this, what are the steps that I might take? Choose the what?
Pick a card for the first 3.
Okay, so pick a rank for the 3 that will have the same rank. Okay, so step 1 is select a rank for the 3 that have the same rank. How many ways are there to do this? How many possible ranks are there? 13. So there's 13 options for that. Step 2, so now I've decided, for instance, here, that I'm going to have 3 7s. So if I want to finish up describing these cards, what's left? Yeah? Sure. Or choose the 3 suits that these things will have, right? So choose 3 suits for those 3 cards. And the number of ways to do that, there's 4 suits. I need to choose 3 of them, which happens to be the same as 4 choose 1, as you've noticed, and we've discussed many times, which is just 4. Okay. All right. Next step. So now we've figured out, this is what's going. These will be the triple part of the full house. Yeah. Yeah. Select a rank for the remaining 2. And now there's only 12 ways to do this. because I can't pick the same rank that I picked here. There's just not enough cards to finish this off. So there's 12 for that. And then finally, so now I've decided that the next rank is we're going to have 2 queens. I need to decide their suit. So that's select the 2 suits for those cards. And there are 4, choose 2 ways to do that, which is 6. Okay. All right, so the set A, we now know has size 13 times 4 times 12 times 6. And so the probability of A is that over 52, choose 5, which is equal to the printer was too slow today. Up on top is 3,744, and on the bottom is 2,598,960, which is approximately 0.00144, which you can write another way as it's about 1.44 out of 1,000. So it's a little more than a 0.1% chance. So between 0.1 and 0.2. So not very likely that you'll be dealt a full house straight off the bat. On the other hand, if you play poker a lot, 1,000 hands of poker is not an outrageous number of hands to have played. So there will be times when you've probably gotten a full house right off the top. Okay. Questions? So now you can do this for all your favorite, all the important poker hands, and you'll realize, go ahead and look at them. You can see them, find lists of poker hands ranked by how strong they are, which ones beat which other ones. And you'll find that if you do these calculations, you realize the better and better ones are just less and less likely to happen. All right. Here's another gambling question that has kind of a famous history. There was a gambler whose name I won't try to pronounce, who basically was coming up with different games that one could play. And he had 3 games in mind. So here's game 1. In game 1, you roll 6 dice and win if you get at least 1 6. Sounds reasonable, right? We already know that when you roll a 6-sided die, at least in our model of it, each of the 6 outcomes is equally likely. So you get 1 chance in 6 of getting a 6. And if you do it 6 times, it seems reasonable that you should get at least 1 6 some of the time. Game 2 is roll 12 dice and win if you get at least 2 6s. And game 3, you may be able to guess what it is by now. You roll 18 dice and win if you get at least 3 6s. Which game would you rather play? And suppose this is big stakes here. If you win the game, you get all the money in the world, and if you lose the game, you get your head chopped off. So it's important. Which game do you think you're more likely to win? So who thinks it's game 1? Okay. And who thinks it's game 3? Okay. Then I conclude that most of you actually don't have an opinion because you can't possibly choose game 2 as a reasonable option, right? Seems intuitively clear that game 2 is not the best game to play. Either you should go further in this direction or further in this direction. But who knows? Sometimes things are counterintuitive. So let's say that the rest of you, which is the majority of the class, thinks game 2 is the best game to play. Of this game. And in fact, we need a reasonable model of each of the 3 games. So, game 1. We roll 6 dice, and let's give them names D1 through D6. So that means that we're looking at some space that looks like this: D1, D2, D3, D4, D5, D6. So each element in our space, it has 6 coordinates, and that is where each DI is in the set 1 through 6. Okay. So what's the size of this set? So this is the easiest kind of application of the product rule. Maybe the only confusing part is that 6 appears twice here, but that just means you can't get the answer wrong. How many choices for D1? 6. How many choices for D2? 6, 6, 6, 6. So by the product rule, the size of S is 6 times 6 times 6. 6 times, which is 6 to the power 6. All right. That's good. Now, what I'm really interested in is this event A. And what's A? A is the D1s through D6 that are possible outcomes such that at least one di is equal to 6. Okay. So I'm interested in the outcomes. These are the winning ones for me, the ones that let me keep my head. If at least one of these is equal to 6, fantastic. Okay. Now, there's no reason to think that there's anything strange going on with the dice. So this is a uniform probability space, or there's no reason to think that it's not, which means that the probability of A is just the size of A over the size of S. So it's going to be the size of A over 6 to the 6. So I need to figure out the size of A. This is the important thing here. Anybody know how we should proceed here? Yeah. Yeah. Yep. So we can use the complement rule, actually the complement rule for counting, which says, all right, let's, rather than figure out the size of A directly, let's look at A bar, the complement of A, which is going to be S minus A, which, if you take an element of S that's not in A, that means there are no 6's in it. So those are the D1 through D6 in S, such that no DI is equal to 6. Now this is a nice set. This is one that we can count actually quite easily just using the product rule, right? So if I have no 6's here, how many choices do I have for D1? 5. How many choices for D2? 5. I can't pick the 6. 1 through 5, 1 through 5, okay? So that says, just by the product rule, the size of A bar is 5 to the power 6. 6 times, I get to choose among 5 different options. Okay. Good. And now, the complement rule says that the size of A is equal to the size of S minus the size of A bar. We know everything here now. That's 6 to the 6 minus 5 to the 6. So we plug that in here. And nicely, this pops up as 1 minus 5 over 6 to the 6. And how likely do you think this is? Give me an estimate of what you would guess between 0 and 1. Of what you think this probability of winning this game is. So actually, this is a pretty good game. You win almost 2/3 of the time, except for that the other slightly more than 1/3 of the time you get your head chopped off. But yeah, I mean, it depends how much your head is worth versus all the money in the world, I guess. All right. So that's game 1. Now let's tackle game 2. Game 2 is 12 dice, and you win if you get 2 6's. So in game 2, S is this tuple of 12 values, D1 through D12. So the elements of S are these tuples of 12 values, D1 through D12. And again, each of them is in the set 1 through 6. So the size of S, if we use the product rule, now there's a chance we can make a mistake. What is it? Is it 6 to the 12 or 12 to the 6? 6 to the 12. Good. At least those of you who spoke out spoke the right answer. I don't know what that means about the rest of you. 6 to the 12 because I have 6 choices for this, times 6 choices for this, times 6 choices for this, times 6 choices for this. That's 12 sixes multiplied together, which is 6 to the 12. All right. A is going to be the subset of S that is the D1 through D12 in S, such that at least 2 DIs are equal to 6. We've already know what's going to happen down here. Probability of A, probability of winning is going to be the size of A over the size of S, which is going to be the size of A over 6 to the 12. So now we need to know the size of A. How do we tackle that? Well, what did we do here? Here we said the size of A is too hard to compute, so we'll compute the size of its complement. And we can try the same thing here. So A bar then is going to be D1 through D12 in S such that at least, at most 1 DI is equal to 6. Right? If there's not at least 2, then there's at most 1. But this isn't quite the same as our last problem. The difference between 0 and at most 1. So how should we tackle it? Yeah. Yeah. That's the sum rule now. It's easier to count the 2 possibilities that are left, which is either there's 0 sixes or there's exactly 1 6. And that's how we can split this thing. So let's say x0 is equal to D1 through D12 in S such that there are exactly 0 DIs equal to 6. And x1, the same thing, except now we want to know when there's exactly 1 DI equal to 6. All right, because we know that A bar is the union of x0 and x1. So A bar, if there's not more than, if there's not at least 2, then there's at most 0, or at most there's exactly 0 or exactly 1. So A bar is x0 union x1. These are disjoint sets because they have different numbers. The elements of this set have no 6s in them. Elements of this set have 1 6 in them, which means that the size of A bar is the sum of the sizes of these two sets. So now we just need to know these two things. All right. Pick 12 numbers between 1 and 6, 12 integers from 1 through 6, but I'm not allowed to pick any 6s. How many ways are there to do that? So there are 5 to the 12 ways because I only have 5 choices for the first one. I'm not allowed to pick any 6s. 5 choices for the second, 5 choices for the third, and so on. What about x1? How can I pick 12 numbers like this, a sequence of 12 numbers like this? Exactly one of them is a 6. Yeah?
5 to the 11 times 6.
Okay. And how did you come up with that?
I picked one of the dice had 6 ways to do it, and then the remaining 11 had 5 ways.
No.
Sorry.
Yeah. So 5 to the 11 gives me a sequence of, that sounds like it describes a sequence of, so really the way to do this is to draw your 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bins. Make a 2-step procedure which says, first thing I'm going to do, so there's exactly 1 6 in these bins. First thing I'll do is decide where that 6 is going to go. How many options did I have? I had 12 options. And the next thing I'm going to do is fill in the rest of the bins, one at a time, each one not using a 6. So that's 5 to the 11 ways of doing that. So this is going to be 12 times 5 to the 11. All right. And so this size of A is going to be size of S minus the size of A bar, which is size of S was 6 to the 12. A bar is this plus this, so that's minus 5 to the 12 minus 12 times 5 to the 11, all divided by 6 to the 12, which is equal to, drum roll, this fraction, which is approximately 0.6187. So the probability of winning game 1 is about 0.6651. Probability of winning this one is about 0.6187. So game 2 is not as good for us. We're less likely to win, meaning we're more likely to lose our head. And if we do game 3, it just gets worse because it's going to look like this. Size of S is 6 to the 18. A bar is going to be the case where we have no 6s at all, or we have 1 6, or we have 2 6s, but we don't make it up to 3 6s. And the size of x0 is, again, 5 to the 18. Size of x1. For that one, we have to choose which of the 18 slots is going to hold our 1 6, and then fill in the remaining 17 slots. And the size of x2. For that, we have to choose 2 of the 18 slots to hold our 6s. So that's 18 choose 2. And then we have to fill in the remaining 16 slots. And if we compute now the probability of A, that's going to be 6 to the 6 minus these guys, 5 to the 18 minus 18 times 5 to the 17 minus 18 choose 2 times 5 to the 16, and all divided by the size of S, 6 to the 18, 6 to the 18, which is approximately equal to, hopefully it's gone to sleep. Do you think better or worse than game 2? Worse. Uh, 0.59743. So our chance of losing our head is now above 40%. So that's the worst game to play. And in fact, if you use this for game n, where you do 6 times n rolls, you'll find that your probability of winning gets closer and closer to 1/2. So it's approaching 1/2 from above. And so the best thing you can hope for is really this game 1.